Alright class, today we're in section 10.2, which is arcs and chords. Some of what we're going to see today is vocabulary you actually saw in chapter 11. Since we did these chapters out of order, some of this we already know. But I want to do a quick refresh, make sure we remember how to do all of that, and then we've got a little new vocabulary and one new postulate to take a look at today as well. So let's start off with central angles. We know that a central angle is an angle whose vertex is the center of the circle. So really there's an infinite number of central angles we can draw. As long as that vertex is the center of that circle, then it's going to be considered a central angle. And the measure of that central angle is the same as the measure of its intercepted arc. Alright, we've taken a look at minor arcs and major arcs. Minor arcs will be a part of the circle that measures less than 180 degrees. They're named by their endpoints only, and it's going to be the same as the measure of its central angle. When we talk about a major arc is part of the circle that's somewhere between 180 and 360 degrees, so it's a larger angle that we're going to be taking a look at here. Usually we don't name central angles by something that's more than 180 degrees. So when we name them, first of all, we name them by their endpoints and by a point that's on the arc. But their measure, since we wouldn't just say that a measure of a central angle will be larger than 180, we would say it's the difference between the 360 degrees and the measure of its associated minor arc. So we're figuring out the difference to figure out what portion of the circle is left, how many total degrees would be remaining for this major arc. A semicircle is going to be equal to 180 degrees, and those are going to be named similar to major arcs with their endpoints as well as a point on the arc. Okay, so I've got up here an example where we can see some degrees that are already marked. If you go ahead and take 360 minus the rest of these, it should give you the measure of this angle, which would end up being 145 degrees. So that's going to help us when we're taking a look at some of these examples. First of all, central angles are going to be any angle whose center is the vertex of that angle. So we could talk about, and we wouldn't call any of these just angle P, even though P is our center, because there's lots of segments coming off of angle P. So we could talk about angle SPT. We could refer to angle TPW, angle WPQ, angle SPQ. There's lots of central angles that we could name here. Really, angle QPT would be another example of a central angle. Central angles are typically less than 180 degrees, so we wouldn't want to name any straight angles here. Now, minor arcs are going to be those arcs that, again, are measures that are less than 180 degrees. So I could talk about arc ST. We know that its central angle is 62. That's also the same as the measure of its associated arc. So we could say that this arc ST is also 62 degrees, which is less than 180, so it's a minor arc. Arc TW is another example of a minor arc. It's less than 180. Arc QW is another minor arc. It's less than 180. Arc QS is also less than 180. There's also, again, arc, if I take a look at angle QPT, that angle measures less than 180, so would arc QT. Now when I say arc QT, notice that I know I'm talking about the minor arc because I, first of all, only named it with two endpoints. So it has to be going the minor arc direction, not the major arc direction. When we're talking about major arcs, we want, again, arcs that are more than 180 degrees. Obviously less than 360 because they still fit inside of the circle. So when I take a look at some major arcs here, I could say SQT, going all the way from point S to point T around the circle, but going through point Q. That would be considered a major arc. I could have also named it SWT, by the way, as well. It doesn't matter which point you choose that's on that arc as long as there is a point on the arc. Another example would be arc, let's see here, QWS, or arc WTQ. There's lots of major arcs. As long as we're kind of getting the idea, they have to be greater than. Now there's only two semicircles. If you check some measures here, SQW would equal exactly 180 degrees along with STW. Semicircles have to be exactly 180 degrees. we've reviewed some of the older vocabulary that we've seen before, I want to talk about one new vocabulary term and then also our new postulate. First of all, congruent arcs. Congruent arcs, two arcs of the same circle or of congruent circles will be congruent if they have the same measure, same angle measure, same central angle measure. So again, they have to be of the same circle or of congruent circles. So if you take a look at this first example, obviously I'm looking at arc AB and CD. AB and CD are on the same circle, so they meet that criteria. Do they have the same angle measure? Yeah, they're both 45 degrees. So are these arcs congruent? Yes, they are, because they have the same the same angle measure, same central angle measure, and because they're on the same circle. So these arcs are definitely going to be congruent. Now, if I take a look at the arcs AB and CD on this example, the question is, are they congruent? Well, they're not on the same circle, but if you notice, their radius are congruent. And as long as they have a congruent radius measure, then yes, those are congruent circles. So these are two arcs of congruent circles, and they have the same measure, so these, yes, are going to be congruent arcs. Now, take a look here. Arc AB and arc CD. Those are definitely not on the exact same circle, and I know they're not on congruent circles because one's radius is part of a segment that's on the other's radius, so they're not the same radius either. So these two would not be an example of congruent arcs. Alright, our postulate. It's arc addition postulate. Kind of reminds us of like segment addition postulate and angle addition postulate. It says the measure of an arc formed by two adjacent arcs, they have to be adjacent, right next to each other, is going to be the sum of the measure of each of those arcs. So, for example, here I could say the measure of arc ABC, and that's talking about going from A all the way around to C. B is a point that is on that arc. That measure will be equal to the measure of arc AB plus the measure of arc BC. Those are the two adjacent arcs that together form that larger arc. And that's what we call our arc addition postulate.